Thanks, Mike. So yeah, this talk is about work collaborated with my colleagues at Huazhong University of Science and Technology and also University of Central Florida, and also for the similar kind of visa problems. So the first author cannot come here, so I presenting the work. So, well, thanks for Xiaofei. Well, persistent memory is important. Everybody should already know that. Also, have some competing properties. Now, crash consistency is a main concern about the usage of persistent memory. So here is a simple example. So suppose we have two bank accounts, A and B. And if a user actually wants to transfer some money from one account to another account. Now, the CPU, this code is running on the CPU fetches data into cache. And then the transfer started by updating the balance. But everything happens in the cache. Now, suppose at this moment, there's a crash happens. So, no, well, suppose, actually not, sorry. So it's part of the data already reached the persistent memory, but not all of them. Now, if there is suddenly system crashes, and then on the reboot, the persistent memory would have inconsistent data. Now, persistent memory transaction is something people have already proposed a common construct to provide preventions of such kind of problems. It is a piece of code, so it has simple grammars. You put this tx begin, tx end at the front and end of this transaction. What's going on? Sorry. Okay. All right, so then we annotate, add these constructs. Okay, so this is a problem, technical problem. I think this kind of connection problems probably actually froze my computer. Sorry. Yeah, this is pretty bad. I have to reboot my computer. Yeah. Okay, so hopefully the problem is solved. So well, it's interesting. We were talking about the crash. So here's a crash. Good demonstration. And by the way, this computer does have persistent memory. All right, so we have this problem. We talk about Yeah, so there is a crash, and then after this, then we have an inconsistent state, and we can use persistent memory transaction to prevent this inconsistent problem. And what happened actually is when you have these transactions inserted, constructs inserted, then compiler will insert these logging instructions before you update the data. And what is important is after you insert the logging, a compiler inserts logging instruction, it also inserts flush and fence, memory fence instructions. Why do we, because this actually will ensure before you really update the data value, the old value of the data already put into the persistent memory. And also there is a flush at the end of the transaction. What happened is if you have the crash in the middle of the transaction, then these log, because we already record the old values in the persistent memory, we can use those old values to recover the state of the persistent memory into a consistent state. So essentially roll back all of the updates. Now, the problem with this is, well, the log takes time and incurs lots of memory writes and altering problems. So here is some measurements using Intel PMDK library. So that could cause 1.4 to 4.6 times slowdown. And then there have been some efforts trying to reduce the overhead. But even with those, the overhead is still very substantial, over 160 times. No, 160%. Now, basic idea of SpecPMT, which is our work, is, well, log data earlier. How do we do that? So instead of putting these log instructions right before the modification of the data, actually, if we have the log instruction before this transaction, we already recorded the value in the persistent memory before getting into this transaction, then we do not need to insert these kind of analog and fancies into the transaction. And what is good about this is we do not, so here is we have two transactions. And when the first transaction updates A and B, and then we start logging their value. This is new value. Now, then for the second transaction, we do not need to insert the fancies, or here, even for the first transaction, we do not need to insert the fancies after the updates of the value A or B. And also, we do not even care whether A or B value will reach the persistent memory by the end of the transaction. The reason is, well, we already have the old values of A and B logged in persistent memory before the transaction. So even if there are crashes or the data hasn't reached the memory after the transaction and the later crashes, that's okay, we can recover it from the log. And that actually will be able to let us to reduce remove the fancy instructions. Now, fancy instructions actually are the major reasons for the large slowdowns overhead. But to do this, we would need to maintain multiple copies of those old values of some variables. And that's called a stale problem. Some logs actually becomes out of date, but still we have to keep them. Now, how to solve this problem? Now, we introduce an automatic log reclamation. So each is like a GC, but it actually does it in a more efficient way. So it's a background thread. It takes a sequence of log records in chronological order. So it's like what we showed on the bottom of this slide. And there's whole log blocks and in the order of time. And then for each date, only the most recent log record is useful. And then, so when the GC happens, reclamation happens, then we just scan backward and then find those that are already out of date, and then we can reclaim those, place those memory. And we also have optimization introduced called hybrid logging. Hybrid logging, the basic idea is, the purpose of doing this is still to reduce those logging space overhead. And well, how to do that? We separate the data in the memory, in the program into code data and hard data. And then for the code data, we would use undo logging, the traditional undo logging. And then for the hard data, we would use our speculative logging approach. And actually, in our paper, we described all of the mechanisms to make these two work seamlessly together as a synergy. And what is good about this is because we are using the expensive, costly undo log only for code data, so the overhead is very well controlled. At the same time, user can adjust this hardness, what's the threshold to determine whether how much memory you really need to use. And then the one question would be, how do you efficiently find out what data are hard, what data are cold? And the approach we do is use hardware extensions, simple hardware extensions. For TLB, we add some extra counters, and which would be able to count how many times the TLB entry has been accessed. Now, any data that missed in the TLB would be treated as code data. And so that's a way to distinguish them. And some results so this speculative PMT can be implemented in both software and hardware. And this is for software implementations on the real machine. This is used Intel first generation Optane memory. And we compare to Intel PMDK and also two other software approaches published representing state of art. And our approach actually can achieve 5.1 times speedups compared to PMDK, and also significant speedups over the other methods. And then for hardware solution, so we have this comparison with, again, two state-of-art hardware solutions, HOOP and EDE, and the speedups also substantial here. And also, because we talk about the cold and hard, these kind of this threshold, so you can adjust that, and then you would use, that's a trade-off, how much speed up you can get compared to how much memory overhead you will use. So in conclusion, undo logging incurs large overhead due to strict ordering and extra write traffic. Speculatively log data earlier proved to be useful, and it can reduce those memory fences, remove those memory fences, and so they can improve memory performance, this logging performance. And it can be implemented in both software and hardware. Yeah, thanks for your attention.